Hello everyone. So today we are going to see the problem of the day of lead code. The problem given here is maximum number of moves in a grid. So here we will see that here we are given a grid of positive integers, and here we can traverse from first column of the matrix to the next column if and only if the row minus one position, the row position, and row plus one positions are greater than the current element, right? For example, if we see for 2, then we can see 4 is greater than 2, this 4 which is in the same row, and this 4 which is at row plus 1 position but column plus 1. Yeah, we are seeing all these numbers for column plus 1. This is fixed, right? Column plus 1 is fixed. So if we see for the first example, we can see from 2 we can go for 4, then from 4 we can go to 9, and then for 9 we can have options for 5, 3 and 11, but 11 is the valid one because it is greater than 9, so we can go to 11. So such a way we can traverse all the columns. For example, let's suppose we are having test case like this. Okay, so for example, let's take this test case in our notes and try to understand. Okay, so let's suppose this is our test case, and in this we can go from 3 to 4, and then 4, from 4 we can't go anywhere, right? So from this, from 3 we are getting number of columns till 1, right? It is zeroth column and 4 is that first column, so our answer from this will be 1. If we search from 4, then we don't have any options because we can't go for 4 here, we can't go for 1 here, and we can't go for 1 here, right? After that, if we see for 1, then we don't have any options because all these numbers which are at row minus 1 and row, these positions are having the similar values which is not greater than the current element. That's why we can't traverse from this, and our answers from these columns will be just 0, and from 3 we are getting we can traverse till first index, right? So from here we are getting answer as 1. So first of all, when I saw the problem, I thought just that it can be like, we have, if we can traverse, we have to, we can traverse till the last, otherwise we can't break the path in between. But it is not so, we can traverse as much as possible. For example, in this case we can traverse till first column only, so we can consider this path like we can make only one move. So this can be considered as our answer. So such a way we have to think and try for all the possible ways. So okay, there are so many possible ways because from one position we are starting from the first column, right? And from first column we can have, for each element we can traverse, we can have three ways. So each element will have three ways, and at every point we are having three points, right? Three valid ways to traverse. So we are having so many possible ways, so we have to traverse all those ways and find out the valid ways, and from this we can get what are the maximum number of moves we can get, right? So if we see, this is a recursive type of problem, and if we try to optimize this further, then we can apply some DP and tabulation forms also. So firstly, we will try to do this with recursion and we will optimize further, right? So firstly, we saw that we need to get all the possible ways because there is not any greedy type of approach like we are getting maximum out of numbers, and then we will have this is the only thing which is maximum till now. It's not the way. Here we can get many possible ways, so we have to try all the possible ways. So let's see the constraints as well. So here we are having constraint of grid length, grid length and yeah, grid length of m and grid of I of length as n, and these can vary from 2 to 10 2 to 1000, and multiplication of the row and columns, number of rows and the number of columns, must be less than 10 to the power 5, and grid value is varying from 1 to 10 to the power 6. Okay, so if it is so, we can firstly, let's start with the recursive approach, and we will search for the optimized solutions as well, right? So let's start the coding part. So here we will take n is equal to grid dot length, and m is equal to grid of 0 dot length, and from here we can see we have to take care of the all the values of the first column, or the zeroth column if it is zero indexed matrix. So we will take care of each and every values of first column or the zeroth column, as it is a zero indexed matrix. So we will start traversing in each and every element of the zeroth column, zeroth column. So I less than n, I plus plus, and we will make sure that we will get the maximum of all the answers, right? So cnt, and here we will make a function recursion, and in this we will pass grid, our value of I, and j will be fixed because we are checking from the zeroth index, right? And now here, from here we will just return our cnt, the number of counts or the number of moves. We can put here name as moves. Yeah, so let's see the recursive function. So from here we will return, our return type will be integer, and here we will take a grid, the row and the column, right? So basically we are trying to get the number of moves. The number of moves is equal to number of columns so far we have traversed, right? So whenever we will just try to return anything, we will just return maximum number of columns we have traversed till now. So we will just return the column or our C value here. So okay, so let me copy these values. N is equal to grid dot length, and m is equal to grid of 0 of length, and here we will keep our temporary value or the number of moves, temporarily moves, as C, and we will check all the three possible ways for each and every elements. So if our C plus 1 is less than m, it means that if we are at any position from like C plus 1 must be less than M. It means not the last column. We will not call our DFS or recursive approach, recursive call from the last column. That's why we will just put the limitation here, and after that we will put that R should be less than 0, R should be greater than 0, and here we will put a mark if r minus 1 and c plus 1 C plus 1 is greater than grid of the current element. Yeah, it means grid of R and C. If the R minus 1 positions element is greater, then only we will call the recursive uh, function here. So here our temp will be math.max of its own value and the function we are calling here, right? And the similar approach will be followed for if r plus 1 is less than n and r plus 1, and here also we will check for the r plus 1 condition, and here the same row, right? So all the three possible ways will be checked and maximum value will be kept in our temporary value, right? And after that we will just return our temp value. So once again, let's summarize how this solution is working. So basically we will call each and every values from the first column or zeroth column. It is a zero indexed column, so zeroth column. All the elements will be called uh, having its own recursive function. From 2 we will call one recursive, then 5, then 3, and then 10, right? And after that we will check all the three possible ways. Only if the numbers or the rows and columns are within the boundary and the next number is strictly greater than the current number, then only we will apply the recursive call, right? And our temporary answer is C here. Why? Because let's suppose we are not we couldn't traverse any of the condition, then it means that we reached till the current element, so the current column should be returned as our maximum moves. The temp will hold the value of C as our answer. So let's try to run and submit it, and after that we will see the time complexity and space complexity. Okay, so here our CNT should be replaced with moves. Okay, here we can see time limit exceeded because the last test case is huge, and we have to think for what is the time complexity here. So we are calling each and every elements, and for each and every element we are calling three approaches, right? Three ways, number of possible ways. So maximum from each and every time, 3 to the power n will be called, right? So we have to decrease this time complexity, so we will apply a dp here. So int dp, and how we will decide the dp indexes and what is the size of the dp. So here we can see each and every grid is having a value. Like let's suppose we have already traversed 4 from 2, and 4 is holding some value, like what are the maximum number of columns it already traversed. So when let's suppose here it is 3, so when 3 will call 4, then 4 is already traversed and calculated its values, right? So it will just show like, yeah, I have traversed, so you take my number. So 4 will give the calculated value to 3 if it is 3 here. So here we can see that each and every grid value can have some values inside it, right? So that's why we will have size of n and m, n comma sorry, n multiplied by m, right? And initially the dp value will be initialized with -1 such that we can traverse whether it is already traversed or not. So here we will put the values of values of dp as -1 initially, and we will pass our dp inside our recursion recursive function, right? So here we will pass, and here before going to the any operation we will check whether our dp is already traversed or not. So if it is traversed, then we will just return our current value. If it is not traversed, then we will just do the operation and we will update the dp value at there, right? And now it is much more optimized because of we are not traversing each and every value once again. If it is already calculated, we will just return the values from there only. So here our time complexity is reduced to n square or n into m, because the dp array has its size of n into m, right? So let's try to run it and we will see. Okay, we are getting some. Okay, we have to pass our dp here. Yeah, let's try to submit it. Yeah, it got accepted and it is beating 100%. So here we have saw that our time complexity and space complexity both are of n into m, right? So this was for today's POD. I hope this explanation and approach is helpful to you. Thank you.